this problem we have a flow system, right? So in this problem we have a system where we have a stationary pipe with a 90-degree bend, right? And we need to find the external bracing force necessary to maintain this pipe that has a flow velocity and a cross-sectional area. And so what that means is we have fluid flowing into the pipe and then fluid flowing out, right? We need to find the force capable of actually keeping the pipe stable as this fluid is actually going through, and again it has a flow velocity of v and cross-sectional area of a, right? And so this is very similar. We're going to use something, we're going to create an expression that is very similar to this momentum balance equation, right? And so let's start with this variable right here, right? Well, first off, we need to recognize that the absolute velocity going into the pipe is equal to the flow rate over the cross-sectional area, right? And so we keep that in mind. Now, assume that this equation will be 0 since this is a balanced equation, so we're going to set 0 on the left. And so the force, the initial force is actually the fluid initially flowing into the pipe, and as you can see, if we put this here, this is the y direction, this is the x direction, these are both in the positive directions, right? And so we can see that with the fluid flowing in this direction is going in the positive x direction, so we'll write this as fx, right? And so here, for the velocity in, we're just going to put in the absolute velocity as velocity in. But what about the dm, the d of the mass going in over dt? How do we get that? So the d of the mass going in over dt, this is equivalent to the density of the fluid times this by the absolute velocity of the flow times this by the cross-sectional area of the actual pipe. So we can actually place this in place of d of m going in over dt, so we can write that in its place, right? And so now f of x, we can see this will represent the force of the pipe working against the fluid so that it can actually maintain its position, right? Without this f of x, then this pipe would just be moving constantly in the x direction. So this f of x is preventing any movement going in the x direction. So just simple rearrangement happens in this, sorry. And so what you get is negative rho times this by the absolute velocity squared times this by the cross-sectional area. And this is the bracing force in the x direction. As you can see, it's a negative direction because the fluid is pushing in the positive direction. Now we need to focus on this flow of the system. So you can see this flows in the y direction. So we're going to set up the equation for that very similar manner as we did for we're setting up the bracing force for the y direction very similarly as we did for bracing force for the x direction. So 0 is equal to f of y for the vertical bracing force. And so we need to recognize that this is the momentum leaving the system. So this will be negative. And then the direction of this flow is in the negative y direction. So we're actually going to place a negative here and write down the same expression as we did for the x direction. And again, this is for the momentum leaving the system. And so again, we're going to rearrange this. And what we get is we actually get the same exact expression for this. Only this time, this represents the bracing force for the y direction. And just to summarize it, as water is flowing into the x direction, there's going to need to be a bracing force acting in the negative x direction at this point, and when it starts flowing down, the bracing force actually needs to go downward because of the negative sign right here. So those two equations represent the bracing force necessary to maintain this stationary pipe.